Hello and welcome back to CS33 Introduction to Data Structures and Algorithms Part 2. We are now on our Module 8 where we will focus about dynamic programming. So compared with our first module for Part 3 where we discussed about 3 different design strategies, for this week we will be focusing on one single design strategy, and that is the dynamic programming approach. This is the first video for the week where we will discuss about the introduction to dynamic programming. We will give a simple example just to explain the concept, and that example is computing the nth Fibonacci number. And for the succeeding videos, we will be discussing problems and their corresponding dynamic programming approach. I will give examples for problems that utilizes linear data structure and those that utilizes non-linear data structures. Yung iba uses array, yung iba naman uses adjacency matrix to represent the graph. For this video, it is in fact divided into 2 parts. The first one is the characterization of the problems with a corresponding dynamic programming approach, and the second one is the actual method, how to create a DP algorithm for problems that has specific properties. Okay, so yung specific properties that we will be discussing are the overlapping subproblems and optimal substructure property of a problem. If we have those properties of a problem, then there is a corresponding dynamic programming approach. And those can be addressed using 2 different methods. The first one is the top-down with memoization, and the second one is the bottom-up approach with tabulation. Okay, so this is a slide that explains the concept of dynamic programming. So dynamic programming is a general algorithm design strategy for solving problems defined by or formulated as recurrences with overlapping subproblems. Okay, so we have 2 important concepts in this definition. The first one is problems defined by or formulated as recurrences. So these are just recursive definition of the problem, but the recursive definition of the problem relates the general problem to sub-problems, okay? And the sub-problems has overlaps. So yun yung definition ng dynamic programming. And in fact, these 2 different concepts are the properties that I mentioned a while ago. So this approach is actually invented in the 1950s by an American mathematician, Richard Bellman. So if you're familiar with the Bellman equation, siya rin yung nag-invento nun. Richard Bellman used the term programming for the reason that programming is a buzzword in the 1950s, just like AI ngayon. So we have this general idea of the dynamic programming approach. Number 1, if the problem has those properties as mentioned a while ago, you can actually have this recurrence relation. Okay? The recurrence relation that describes the solution to a larger instance with respect to the solution to some smaller instances. And since we are solving a recursive definition of a problem, we can have solution to smaller instances. We record that solution to a table or to some memory location, and then we extract the solution when needed. So probably it's not very chewable from this perspective, but our main intention in the succeeding slides is to dig deeper into the definitions and concepts that is mentioned here in this slide. So again, if we try to dissect the definition, it has 2 different concepts. The first one is the breaking down of one problem into simpler subproblems. And the second one is the fact that the optimal solution to the overall problem depends upon the optimal solution to its subproblems. This technique has 2 characteristics. The number 1 is that dynamic programming approach addresses the problem with overlapping subproblems and utilizes the property called the optimal substructure property. So to illustrate the first characteristic, that is the overlapping subproblems, let's use the Fibonacci sequence. So the problem is, given an input that is an integer n, we output the nth Fibonacci number denoted by capital F of n. So suppose our input is 3. Okay, so the output should be 2. Or if our input is 4, then the output should be 3. So by definition, this Fibonacci sequence is defined by a recursive function with base cases and the general definition of f of n. So for the base cases, we have f of 0 is 0, f of 1 is 1. But for the general case, f of n is defined by f of n minus 1 plus f of n minus 2. We have a larger instance, which is the general problem, and then the subproblem is f of n minus 1. Another subproblem is f of n minus 2. But how can we say that this has an overlapping subproblems? Let's see by checking this example. So to find the fourth Fibonacci number, since there is a recursive definition of the Fibonacci number, then we can create a recursion tree. So fib of 4 is obtained by getting the sum of fib of 3 and fib of 2. So this is n minus 1, this is n minus 2. But to define this, we need to go deeper dun sa recursion tree and define fib of 2 and fib of 1. This has a constant value if nasa base case na tayo. Okay, so for the leaf of the recursion tree, we can actually see that the evaluation stops if the return value is already a constant. Okay? And then you can go up the tree to define fib of 4. So the concept of an overlapping subproblem for the Fibonacci sequence. So for you to get fib of 4, you need to compute for this one and this one with overlapping subproblems, because fib of 1 is called here as well. The second characteristic of dynamic programming is optimal substructure property. So according to the definition, any problem has optimal substructure property if its overall optimal solution can be constructed from the optimal solutions of its problem. In this case, we don't have an optimization problem, so the concept of the optimal solution here is the exact computation of f of n. So since we can get the f of n using the exact solution for f of n minus 1 and f of n minus 2, this has an optimal substructure. Another example with an optimal substructure property is the problem of finding the shortest path. So suppose the problem is you need to identify the shortest path from start to goal. And if the shortest path is start, then A, then B, then goal, and we change the problem to from A to goal na lang, you can see that the shortest path from A to goal is a subset of the shortest path from start to goal. So the optimal solution for the smaller instance is used to get the optimal solution for the larger instance. And not all problems have this property. So the next question is how to know if we can apply a dynamic programming approach for a particular problem. The simple answer is if a problem has an overlapping subproblems and has an optimal substructure property, then we can create a dynamic programming approach, because these are the necessary characteristics that DP is addressing. So the main idea for the dynamic programming approach is, number one, set up the recurrence relation, a relation that relates the solution to a larger instance to a solution of smaller instances. And this is impossible without the two properties mentioned a while ago. And then solve the smaller instances only once, record the solution in a table, and extract it whenever it's needed. Okay, so there are two approaches to solve this problem. The first one is the top-down with memoization, and yung inverse naman niya is the bottom-up with tabulation. And before we present the pseudocode for the dynamic programming approach, let's go back to the brute force algorithm for the problem. So given that the definition of f of n is recursive, then we can create a recursive algorithm corresponding to that definition. This is the base case, and this is just for the general definition of f of n. F of n is equal to the f of n minus 1 plus f of n minus 2. So to visualize what is happening in this recursive algorithm, then there is a corresponding recursion tree that enumerates what is being called. And as you can see, since this has an overlapping subproblems, multiple calls to fib0 is done, multiple calls to fib of 1 is done, and so on. The running time for this recursion tree is the total number of nodes in the tree. And if you recall how to compute for the running time given a recursive algorithm, then one method is guessing and then proving by mathematical induction. So the guess here is O of 2 raised to n. Why? Because the height of the tree is n and the total number of nodes in the tree with height of n is 2 raised to n. So if we have that guess, if you prove by induction, you can also prove that the guess is correct. So we can improve this brute force algorithm by doing the first approach, the top-down memoization. So the way how to do it is to create a container for the memoization and modify the recursive definition to check if a particular subproblem is already solved and is available. And then for every computation, store the content in the container if it's not yet there, and if it's there, retrieve the content. So what we will do is to have a modified version of the recursive algorithm, but number one, you need to create a container for the memoization that has length n. Negative 1 here is to illustrate that the content is not yet computed. And then we use this container for the recursive definition of the problem. And the recursive definition of the problem is here with the base case in lines 7 to 8. And then we simply modify the way how it is called in the recursive definition by utilizing the content of the memoized table. So to illustrate the algorithm presented in the previous slide, let's use the same recursion tree from our previous example. So this is the content of the memoized table with negative 1 to indicate that the answer to the computation is not yet obtained. Instead of calling each fib of I multiple times, since we store the content, we are guaranteed to compute each fib of I only once. With this implementation, we can make sure that there is no repeated calls to fib of I, and thus reducing the total number of computations necessary to compute the fib of n. The computation stops if the fib of n is already computed. The second approach is by bottom-up with tabulation. So this is much more straightforward compared to the memoization because this is a computation that starts from the base cases and then filling up the table until fib of n is reached. So the tabulation is actually the opposite of the top-down approach, and this approach is not using a recursive definition. In this approach, we solve this by filling up the table from index 0 up to index n. Okay, so this is the code for the bottom-up approach with tabulation. As you can see, this algorithm is not recursive, and in fact, it is an iterative algorithm that starts with the base cases and then filling up the table one by one up until we reach the parameter n. And the definition inside the iterative part of the code is just the definition with dp of I is equal to dp of the smaller instances I minus 1 and I minus 2. The algorithm stops if we reach dp of n. Okay, so this is an example computation for the nth Fibonacci number. Again, we will start with 0 and then 1 as the base cases, and then for the second, third, fourth, and so on, we simply compute the sum of the two consecutive numbers. So to get this number, we need to get the sum of this and this. And in general, to get this number, we need to compute the sum of these two consecutive numbers. So the running time of the bottom-up approach is the running time of filling up the table, and that running time is actually linear in n. So if we compare the brute force algorithm for this problem, we actually reduced the running time to linear. So from 2 raised to n, we obtained a better running time of O of n.